The sonar operator pressed his headphones tighter against his ears, listening for the telltale ping that would reveal the submarine lurking somewhere in the darkness below. He had been at this for 6 hours now, hunting a ghost that kept slipping through his fingers like water through a net. The convoy of Allied merchant ships behind him carried food, ammunition, and fuel desperately needed in Britain. Somewhere out there, beneath the gray waters of the English Channel on this August morning in 1944, a German U-boat was stalking them. He could feel it. The equipment said it was there. And yet, every time his sonar swept across the area where the submarine should be, the echo came back wrong. Too quiet, too distorted, like trying to see through frosted glass. 3 hours later, HMCS Alberni, a Canadian corvette with 90 men aboard, would vanish beneath the waves in less than 30 seconds, torn apart by torpedoes from a submarine that sonar never properly detected. The U-boat that sank her was covered in something that should not have worked. A coating of synthetic rubber just 4 millimeters thick, perforated with thousands of tiny holes in a pattern that seemed absurdly simple. The Germans called it Alberic, after the dwarf from Norse legend who possessed a cloak of invisibility. Allied naval intelligence would soon learn that this seemingly primitive solution, this rubber sheet with holes punched through it like a fisherman's net, was defeating the most sophisticated underwater detection system ever created. This is the story of how that coating came to be. But it is really about something deeper, about the moment when desperation forces innovation, when conventional thinking collides with impossible problems, and when the solution turns out to be hiding in the fundamental physics everyone thought they understood. And what it reveals about war is this: sometimes the difference between victory and death is not better technology, but the willingness to question every assumption, to see connections others miss, and to pursue ideas that sound ridiculous until they save lives. By 1940, the Battle of the Atlantic was becoming a war of invisible hunters and increasingly sophisticated prey. German U-boats were strangling Britain's supply lines, sinking merchant ships faster than they could be replaced. The Kriegsmarine had perfected the art of the wolf pack, coordinated submarine attacks that could devastate entire convoys in a single night. But the Allies had developed a weapon that threatened to turn the tables completely. It was called ASDIC by the British, Sonar by the Americans, and it worked on a principle so elegant it seemed unbeatable. Send a pulse of sound through the water. When it hits something solid, a submarine's steel hull, it bounces back. Measure the time it takes for the echo to return, and you know exactly how far away the target is. Point the transducer in different directions, and you can locate the submarine precisely, enough to drop depth charges that would crack its pressure hull like an eggshell. For submarine commanders, ASDIC represented an existential threat. The ocean, once an invisible refuge, had become transparent. U-boats that had prowled with near impunity now found themselves hunted, tracked, and destroyed with increasing efficiency. By 1943, the tide was turning. More U-boats were being sunk than ships they destroyed. The strategic calculus that had made submarine warfare so effective was collapsing. And so, in laboratories scattered across wartime Germany, scientists were tasked with an impossible problem: not to build a better submarine, not to develop more powerful torpedoes, but to make a submarine invisible to sound itself, to create, in effect, an acoustic cloak. The man who would solve this problem was not a military engineer or a naval officer. He was an academic, a physicist named Erwin Meyer, one of Germany's leading acousticians, working at the Kaiser Wilhelm Institute and later at the University of Göttingen. Meyer was a careful, methodical researcher whose interests ranged across the entire spectrum of acoustics, from architectural design to measurement techniques. He was not, by temperament, a weapons designer, but war does not respect temperament. In 1940, Meyer's research group received orders from the Kriegsmarine. find a way to reduce the acoustic signature of submarines, make them harder to detect with active sonar. The stakes could not have been clearer. Every percentage point of reduction in sonar effectiveness translated directly into German sailors coming home alive and Allied convoys reaching the bottom of the Atlantic. Meyer understood the physics of the problem with the clarity that comes from years of studying how sound moves through different materials. When an ASDIC pulse hit a submarine's steel hull, most of that acoustic energy bounced straight back to the hunting destroyer above. Steel and water have vastly different acoustic impedances, different resistances to sound wave propagation. At that boundary, sound behaves like light hitting a mirror, almost perfect reflection. To defeat sonar, you needed to do one of two things. Either prevent the sound from reaching the hull in the first place, absorbing it before it could reflect, or scatter and distort the return signal so completely that the sonar operator could not distinguish the submarine from background noise or natural phenomena. Meyer chose both. The solution he developed seemed counterintuitive, almost childlike in its simplicity. Take synthetic rubber, specifically a material called Opinol, manufactured by the chemical giant IG Farben. This was a specially formulated polyisobutylene polymer with unusual properties. It remained elastic even in cold water, critical for submarines operating in the North Atlantic. More importantly, it could be manufactured with precise internal structures. Meyer's team created sheets of this rubber roughly 1 meter square and just 4 millimeters thick. Into this rubber, they engineered thousands of tiny air cavities and punched cylindrical holes in carefully calculated patterns. Some holes were 2 millimeters in diameter, others 4 millimeters, arranged in specific geometric relationships. To anyone looking at these perforated rubber sheets, they might have seemed like fishing nets made of rubber. Simple, almost primitive. A technology that fishermen had been using for thousands of years, nets with holes to let water flow through while catching fish. But Meyer understood what was really happening at the acoustic level, and it was anything but simple. Each air cavity, each hole, each boundary between rubber and air and water created a resonant structure. When a sonar pulse hit this coating, several things happened simultaneously. First, the rubber itself absorbed some of the acoustic energy, converting it to heat through internal friction and molecular motion. Second, the air pockets acted as resonators. Sound waves entering these cavities would bounce around inside, their energy dissipating with each reflection. The specific sizes and spacings of these cavities were tuned to the frequency range of Allied ASDIC systems, typically between 10 and 18 kilohertz. At these frequencies, the cavities would resonate, trapping and absorbing sound like a series of tiny acoustic black holes. Third, the holes and irregular surface scattered the remaining sound in multiple directions. Instead of a clean, strong echo returning to the sonar operator, the signal that came back was fragmented, distorted, weakened by about 15% compared to bare steel. 15% does not sound like much. In a world of ones and zeros, of detection or no detection, 15% seems like the margin of error, a minor improvement. But in the gray, ambiguous world of submarine warfare, where sonar operators were trying to distinguish real contacts from thermal layers, schools of fish, wrecks on the seafloor, and the acoustic clutter of a busy ocean, 15% was the difference between certainty and doubt. It was the difference between a destroyer racing toward a confirmed contact and a commander deciding the signal was too weak, too uncertain to justify breaking away from convoy protection. It was the difference between life and death. The first U-boat to receive this coating was U-11, a small Type IIb submarine in 1940. The initial tests were promising enough to continue development. But as with many wartime innovations rushed from laboratory to battlefield, the gap between theory and practice yawned wide and treacherous. The first operational submarine to carry Alberic into combat was U-67, a larger Type 9 boat. In April 1941, after completing her first war patrol, U-67 put into Wilhelmshaven, where engineers spent weeks carefully applying the rubber coating to her conning tower and hull sides. The process was painstaking. Each sheet had to be precisely aligned, then glued and riveted into place using adhesives that could withstand the crushing pressures of deep diving and the corrosive assault of seawater. By May, U-67 was conducting trials in the Baltic Sea near Kiel, and almost immediately the problems began. During the voyage from Wilhelmshaven to Kiel, about 25% of the coating simply fell off. Sheets of rubber peeled away from the pressure hull, flapping in the water flow, creating turbulence that made the submarine easier to detect, not harder. The adhesive, it turned out, was not strong enough. The bond between synthetic rubber and steel, subjected to temperature changes, pressure cycling as the submarine dove and surfaced, and the mechanical stresses of ocean travel, was failing catastrophically. Worse, the coating that remained was slowing the boat down. The added drag from even a 4mm thick coating across the submarine's entire surface was reducing speed noticeably. For a vessel whose survival often depended on being able to outrun depth charges or reach attack position quickly, this was unacceptable. The sonar trials themselves produced ambiguous results. Testing in Norwegian fjords showed some reduction in both the submarine's own noise and its detectability under active sonar. But quantifying the exact improvement proved maddeningly difficult. Water conditions varied dramatically. Temperature layers in the fjords created acoustic ducts and shadow zones that made consistent measurements nearly impossible. One test would show promising results. The next, conducted in slightly different conditions or at a different depth, would show minimal effect. By August 1941, the decision was made. Strip the Alberich coating from U-67 entirely. The technology was not ready for operational use. For 3 years, the project languished. Meyer and his team continued their research, but without naval support, progress was slow. The adhesive problem seemed insurmountable. Every formulation they tried either failed to bond properly or degraded in seawater. The submarine war continued, and U-boat losses mounted. By 1943, the Allies had turned the Battle of the Atlantic decisively in their favor. Improved ASDIC, radar, code-breaking, air cover, and sheer numerical superiority in escort vessels meant that U-boat crews were facing a death sentence. Of the roughly 40,000 men who served in the German submarine force during World War II, over 30,000 died, a casualty rate of 75%. This was not warfare. This was industrial-scale slaughter. Desperation breeds innovation. In late 1943, IG Farben chemists finally developed an adhesive formulation that could withstand the operational stresses. It was not perfect. Applying the coating still required thousands of man-hours of careful, precise work. But it held. The coating stayed attached. In October 1943, a Type 7C submarine, U-480, was commissioned under the command of Oberleutnant zur See Hans Joachim Förster. U-480 would become the first submarine to carry the Alberich coating into sustained combat operations. The process of applying the coating was exhaustive. Workers at the Deutsche Werke shipyard in Kiel spent weeks meticulously gluing and riveting the rubber sheets to every exposed surface of the pressure hull and conning tower. Each sheet was 1 meter square. Each had to be aligned precisely. Each seam had to be sealed perfectly. Any gaps, any raised edges, any imperfections would create turbulence and noise that would defeat the entire purpose. The completed coating covered the submarine like a second skin. To the eye, it was unremarkable. Matte black rubber, slightly rough to the touch, perforated with thousands of small holes in regular patterns. It looked, more than anything else, like industrial matting, the kind you might see on a factory floor. Nothing about it suggested cutting-edge stealth technology. Nothing about it looked like invisibility, but U-480 was not designed for looks. She was designed for one thing: to survive in the English Channel, the most heavily defended and intensively patrolled body of water in the world. The Channel in 1944 was a gauntlet. Allied destroyers, corvettes, and frigates crisscrossed the narrow waters constantly. Aircraft patrolled from above, indicator loops, underwater cables that detected the magnetic signatures of passing submarines, guarded harbor approaches. No German submarine had operated successfully in the Channel for months. Most that tried were detected and destroyed within days. The Kriegsmarine sent U-480 into the Channel specifically because of her coating. If Alberic worked anywhere, it would have to work there, under the most challenging conditions imaginable. On her first patrol, U-480 was attacked by a Canadian Catalina flying boat. The aircraft was shot down, but the encounter demonstrated that the coating did nothing against radar or visual detection. It was purely an underwater defense. On her second patrol, departing from Brest in August 1944, U-480 would prove that Alberic worked exactly as designed. August 21st, 11:45 in the morning, 25 nautical miles southeast of St. Catherine's Point on the Isle of Wight. HMCS Alberni, a Flower-class corvette, was escorting a convoy through the Channel. Her ASDIC was active, sweeping the water ahead and to the sides, searching for submarines. The operator heard something. A contact bearing 040, range uncertain. The signal was weak, distorted. It could be a submarine. It could be a wreck on the bottom. It could be a school of fish or a thermal layer playing tricks with the sound waves. The contact was not strong enough, not clear enough to warrant a full attack. Alberni maintained her position with the convoy. Beneath the gray water, Hans Joachim Förster watched through his periscope and gave the order to fire. The Zaunkönig torpedoes, acoustic homing weapons designed to track the propeller noise of escort vessels, were in the water and running hot. The first torpedo struck Alberni on her port side, immediately behind the engine room. For a corvette, a relatively small vessel, the damage was catastrophic. The stern began sinking immediately, dragging the rest of the ship down. 30 seconds. That is how long it took for HMCS Alberni to disappear beneath the surface. 59 of her 90 crew went down with her. Some men made it to the water, only to be pulled under by the suction of the sinking ship. Others drowned in the chaos, weighed down by equipment and heavy clothing. A few survived, picked up by other escorts who raced to the scene. The sonar operator who had heard that weak, uncertain contact would spend the rest of his life wondering if a stronger signal, a clearer detection, would have made a difference. If they had investigated that contact more aggressively, if they had dropped depth charges, if they had forced U-480 to go deeper or move away. If. The questions haunt survivors. But the acoustic physics were clear. The Alberic coating had reduced the sonar return just enough to create doubt. And in war, doubt kills. Over the next 3 weeks, U-480 would sink 3 more vessels: the merchant ship Orminster, the tanker Waipawa, and the British corvette HMS Loyalty. Each time, the pattern was the same: sonar contacts that were too weak, too unclear. A submarine that could approach to firing range without triggering the aggressive response that normally kept U-boats at bay. The coating was working. Naval intelligence officers interviewing survivors and analyzing sonar logs began to notice a pattern. Ships were being torpedoed in areas where ASDIC should have provided clear warning. Operators reported hearing contacts, but described them as unusually weak, with echoes that seemed to fade or distort. Through careful analysis of attack patterns and interrogations of captured German sailors, Allied intelligence pieced together the truth. The Germans had developed some kind of acoustic coating. The exact composition remained unknown, but the effect was clear. ASDIC range was being reduced by at least 15%, possibly more under certain conditions. This does not sound like much, but think about what it meant operationally. An ASDIC system with a nominal range of 2,000 meters was now effectively detecting targets at 1,700 meters or less. That missing 300 meters of detection range translated directly into reaction time. At typical convoy speeds, 300 meters represented several minutes of warning, minutes that could mean the difference between evading an attack or absorbing it. The response from Allied anti-submarine forces was swift and pragmatic. If they could not reliably detect these new stealth submarines with existing technology, they would create conditions where detection was unnecessary. Operation Brazier D2 was conceived as a trap. Intelligence had broken the Enigma code. They could read German naval communications. When U-480 reported her position and intentions by radio in early January 1945, British intelligence knew exactly where she would be. They could not detect her with sonar, but they did not need to. Instead, they laid a secret minefield directly in her projected path, deep water mines moored to the seafloor, waiting. U-480 left Trondheim, Norway on January 6, 1945, for her third patrol. She never returned. Somewhere between January 29th and February 20th, U-480 struck a mine from the Brazier D2 field. The explosion damaged her stern, and she sank in 55 meters of water, 20 kilometers southwest of the Isle of Wight. All 48 crew members died. Helmsman Horst Rüstner survived only because he had been left behind in Norway for training. The wreck was discovered by accident in 1997 by sport divers. The following year, nautical archaeologist Innes McCartney correctly identified it as U-480 through careful examination of the Alberic coating still clinging to parts of the hull in the cold, dark water. That rubber skin, that fisherman's net pattern of holes and air pockets, was still there after more than 50 years underwater. The story of Alberic did not end with U-480's sinking. About a dozen other U-boats received the coating before the war ended, including U-485, U-486, U-1105, known as the Black Panther, and U-4709. Most of these submarines saw limited action. The war was ending. The Kriegsmarine was collapsing. The elaborate plans to coat the new Type 31 and Type 43 submarines with Alberic remained mostly unrealized. There was not enough time, not enough resources, not enough synthetic rubber. But the technology itself survived. After Germany's surrender, Allied technical intelligence teams descended on captured U-boats with the intensity of archaeologists excavating a lost civilization. They cataloged everything, measured everything, tested everything. U-1105, the Black Panther, was handed over to the Americans specifically for detailed study of her acoustic coating. Researchers at the Naval Research Laboratory and MIT spent months examining the rubber, analyzing its composition, testing how it absorbed sound, trying to understand exactly how Meyer's team had achieved such effective results with such apparently simple materials. And then, remarkably, the technology was abandoned. Neither Britain nor the United States adopted anechoic coatings for their submarines in the immediate post-war period. Why? The reasons were complex and revealed something about how militaries process innovation. First, the Cold War submarine paradigm shifted dramatically. Nuclear submarines were faster, deeper diving, and much noisier than their diesel-electric predecessors. The problem was not making them invisible to active sonar, it was making them quiet enough that passive sonar, listening for their own noise, could not detect them from hundreds of miles away. Second, the coating had serious practical problems that German engineers never fully solved. It fell off. Modern Virginia-class nuclear submarines, the most advanced in the world, still struggle with anechoic tile delamination. Submarines return from deployment with large patches of coating missing, exposing bare hull that defeats the entire purpose. If billion-dollar nuclear submarines with advanced materials science and manufacturing cannot keep the tiles attached reliably, World War II-era technology certainly could not. Third, there was a certain institutional skepticism. 15% reduction in sonar return sounded good on paper. But was it worth the enormous cost in time, materials, and maintenance? Submarines could achieve similar or better results through tactical maneuvers, diving beneath thermal layers, operating in acoustically cluttered environments, or simply staying far away from enemy sonar. The coating was a solution, but was it the best solution? For 30 years, anechoic coatings remained a historical curiosity, a technological dead end from a desperate German Navy. And then, in the 1970s, the Soviet Union began coating their submarines with rubber tiles. Soviet naval engineers, studying captured German research and conducting their own acoustic experiments, had concluded that Alberic had been abandoned prematurely. Modern materials and adhesives could solve the delamination problems, and even a modest reduction in acoustic signature, combined with other stealth measures, could provide a decisive tactical advantage. The Victor-class attack submarines were the first to receive comprehensive acoustic coatings. Early tiles were prone to falling off, just like the German versions 30 years earlier. But the Soviets persisted, refining the materials, improving the adhesives, optimizing the cavity designs for different frequency ranges. By the time the Akula-class submarines entered service, their anechoic coatings were reducing acoustic signatures by 10 to 20 decibels. That translates to reducing the strength of the reflected signal to somewhere between 10% and 1% of the uncoated intensity. Suddenly, submarines that should have been detectable at substantial ranges were disappearing into the ocean's acoustic background. The West took notice. The Royal Navy began applying anechoic tiles to their submarines in 1980, starting with HMS Churchill. The United States Navy followed in 1988. Today, virtually every modern submarine in the world uses some form of acoustic coating. The tiles are thicker, more sophisticated, often containing multiple layers with different acoustic properties. But the fundamental principle, trap sound energy in resonant cavities filled with air, scatter what you cannot absorb, remains exactly what Erwin Meyer discovered in 1940. What emerged from German laboratories as a desperate wartime measure has become standard technology, as fundamental to submarine design as the pressure hull itself. There is something both ironic and illuminating about how this technology evolved. Meyer and his team created Alberic under immense pressure, working for a regime that was systematically destroying European civilization, trying to help sailors survive in a war that should never have been fought. The technology they developed was used to sink Allied ships and kill Allied sailors. And yet, decades later, that same technology protects submarines from nations that were once enemies. British submarines, American submarines, even modern German submarines all use descendants of the acoustic coating that U-480 carried into the English Channel. The physics, it turns out, has no politics. Sound waves do not care about ideology or national identity. An air cavity in rubber will resonate at specific frequencies, whether it is defending German sailors in 1944 or American sailors in 2024. The principle is universal. So, what does this story reveal about innovation under pressure, about the collision of desperate necessity and human ingenuity? First, that the best solutions often sound absurd until they work. A perforated rubber sheet, a pattern of holes like a fisherman's net, defeating the most sophisticated detection technology of the era. If you had proposed this to naval engineers in 1939 before anyone had tried it, they would have laughed. Rubber versus steel, holes versus solid structure. It violated intuition. It seemed too simple to work. But physics does not care about intuition. The math said it should work. Meyer tested it. It worked. Second, that the gap between laboratory success and field deployment is enormous and frequently underestimated. The first test of Alberic on U-11 in 1940 was promising, but it took 4 years of iterative development, countless failures, adhesive formulations that did not work, coatings that fell off, before the technology was reliable enough for combat. Innovation is not a moment of inspiration. It is years of grinding, unglamorous problem-solving, testing, failing, learning why you failed, trying again. Meyer kept careful records of every test, every failure. After the war, he hid those records under the attic floor of his in-laws' house in Thuringia, preserving them despite the personal risk, because he believed the knowledge was valuable regardless of who eventually used it. Third, that technology can be simultaneously effective and impractical. Alberic worked. It reduced sonar effectiveness measurably. U-480 sank 4 ships in waters where uncoated submarines were being destroyed within days. But the coating required thousands of hours to apply, used scarce materials, fell off during operations, and reduced submarine speed. It was effective enough to justify using on a few submarines in desperately contested waters. It was not practical enough to coat the entire fleet. The calculus of wartime technology is brutal. Does this save more lives than it costs in resources that could be used elsewhere? Sometimes the answer is yes. Sometimes it is no. And sometimes, as with Alberic, the answer is complicated. Fourth, that good ideas are rarely lost forever, just waiting for the right conditions to re-emerge. Alberic was abandoned after World War II because the problems it solved were no longer the most pressing problems facing submarine designers. But when Soviet submarines became quieter and Western navies needed every possible advantage in acoustic stealth, suddenly the 70-year-old German research became relevant again. The timing was right. The materials science had advanced. The strategic calculus had changed. Ideas do not die. They hibernate, waiting for their moment. And finally, this story reveals something profound about the nature of war itself. At some level, beneath all the grand strategy and political rhetoric and ideological conflict, war is about physics, about thermodynamics and fluid dynamics and acoustics, about what happens when a sound wave hits a boundary between materials with different acoustic impedances, about whether air cavities in rubber will resonate at the right frequency to absorb energy from a sonar pulse. These physical realities do not care about good or evil, about who deserves to win or who is fighting for a just cause. They simply are. A well-designed acoustic coating will work whether it is protecting heroes or war criminals. This can feel uncomfortable, even disturbing. We want technology to have moral content, to be intrinsically aligned with good or evil, but it does not. Technology is a tool. The physics is neutral. What matters is who uses it and for what purpose. Meyer's acoustic research helped German submarines survive and kill Allied sailors in 1944. That same research, refined and developed, now helps protect submarines from dozens of nations, including the democracies that defeated Nazi Germany. The knowledge persisted, the application changed. And in that transformation, perhaps, there is something to be learned about how we think about innovation in general. We celebrate the breakthrough moment, the flash of insight, the lone genius in the laboratory making a discovery that changes everything. But the reality is messier and more collaborative. Meyer did not work alone. He led a team of acousticians, chemists, and engineers. The synthetic rubber was developed by IG Farben chemists. The submarines were built by shipyard workers. The testing was done by naval officers and crews willing to take experimental technology into combat. Innovation is a system, not a moment, and the value of any innovation depends entirely on context. Is 15% reduction in sonar effectiveness worth thousands of hours of application time? In 1944, in the English Channel for U-480, the answer was yes. For the broader U-boat fleet, the answer was no. The same technology, different circumstances, different answers. There is no universal metric for success. Context is everything. Today, if you visit the site, where HMCS Alberni sank in 1944, there is nothing to see. The wreck has been scattered and salvaged. The men who died there are long gone, their names recorded on memorials. If you dive on U-480's wreck, which sits in relatively shallow water and is accessible to sport divers, you can still see fragments of the Alberic coating clinging to the hull after 8 decades underwater. Perforated rubber, full of holes, looking for all the world like some kind of industrial fishing net stretched over a submarine. It is easy to see that coating and think of it as a relic, a curiosity from a war long over. But that would be missing what it really represents. This was the moment when submarine warfare became about more than just better torpedoes and stronger hulls. It was the beginning of acoustic stealth, of understanding that the battle was not just kinetic, but informational. Could you see the enemy? Could they see you? And if you could manipulate the physics of detection itself, you could change the fundamental calculus of combat. Submarines today are shaped by this insight. Their designs are influenced by how sound propagates through water, how materials absorb or reflect acoustic energy, how electronic signals can be minimized or disguised. The coating on U-480 was primitive by modern standards, but the principle was revolutionary. Make yourself hard to see by controlling how information flows. The ultimate lesson of Alberic is not about rubber and holes and resonant cavities, though those are fascinating in their own right. The lesson is about what happens when you question assumptions that everyone else takes for granted. In 1940, everyone knew that a submarine's steel hull would return a strong sonar echo. That was a fact of physics, seemingly immutable. Meyer asked a different question. What if we change what the sonar hits? What if we put something between the water and the steel that disrupts the reflection? What if we trap the sound before it can bounce back? The answer was there in the physics all along, waiting for someone to see it. A pattern of air pockets and rubber arranged just so, tuned to specific frequencies. Simple enough that it might remind you of a fisherman's net. Sophisticated enough that it took decades to fully understand and implement effectively. That is innovation. Not the lone genius and the eureka moment, but the careful application of fundamental principles to seemingly impossible problems. The willingness to try ideas that sound silly until they are tested. The persistence to work through 1,000 small failures to reach a solution that works well enough, even if not perfectly. Erwin Meyer died in 1972, long after the war ended, having returned to academic research and contributed to many fields of acoustics. He never sought credit for Alberic, never promoted his wartime work. In fact, his research group initially believed the coating had never been used operationally. It was not until 1998, when U-480 was identified, that the full story emerged. Meyer had hidden his research notes under the floorboards because he believed the knowledge had value beyond the immediate context of the war. He was right. Those notes, that carefully preserved documentation of how to make sound disappear into rubber and air, became the foundation for technology that protects submarines around the world today. The next time you hear about stealth technology, about aircraft designed to evade radar or submarines that disappear into the ocean's acoustic background, remember where it started. With a desperate German physicist, a team of chemists and engineers, and a deceptively simple idea. Cover the submarine in rubber, punch holes in it, fill those holes and cavities with air, let the sound waves enter, trap them, absorb them, scatter what remains. Make the echo too weak to trust. Create doubt where there should be certainty, and watch as a submarine becomes a ghost, present but undetectable, deadly precisely because it cannot be seen. That is the power and the peril of innovation. It works for whoever figures it out first. It does not care about deserving. It only cares about physics, properly understood and correctly applied. The air pocket does not know whether it is defending freedom or tyranny. It just resonates at the frequency you designed it for, absorbing sound, creating silence, where there should be echo. In the end, perhaps that is what is most striking about the entire story. How something that seems so simple, so obvious in retrospect, a piece of rubber with holes in it, could represent such a profound shift in how warfare is conducted. How the difference between detection and invisibility, between life and death, could come down to millimeters of synthetic material and precisely engineered air gaps. How the ocean, which had always been transparent to those with the right equipment, could become opaque again. 75 years later, submarines still carry descendants of Meyer's coating. Engineers still wrestle with keeping the tiles attached. Navies still debate the trade-offs between acoustic stealth and operational complexity, and somewhere on the seafloor off the Isle of Wight, fragments of the original Alberic coating still cling to U-480's rusted hull, a ghost of a submarine that became a ghost itself, invisible to the technology meant to reveal it. That perforated rubber, that fisherman's net of air, and synthetic polymer changed submarine warfare forever. Not because it was perfect, but because it worked just well enough to matter. And in war, as in life, working just well enough is sometimes all you need to survive another day, to sink another ship, to make it home, or, in U-480's case, to demonstrate that invisible submarines were possible, even if this particular invisible submarine did not survive to see the end of the war. The coating outlasted the submarine. The idea outlasted the war. And the principle, sound can be trapped and absorbed if you understand the physics deeply enough, became a foundation of modern stealth technology. That is the real legacy of Alberic. Not the rubber tiles themselves, but the proof that invisibility, at least to sonar, was achievable. And once something is proven possible, it stops being a fantasy and becomes an engineering challenge. It becomes a matter of time and resources and iterative improvement. It becomes inevitable. The sonar operators who listened for U-480 in the English Channel that August day in 1944 never knew what they were up against. They did not know about Meyer's research or the carefully engineered rubber coating or the thousands of hours spent gluing it to the submarine's hull. They just knew that the echo was wrong, too weak, too uncertain, not quite there. That uncertainty got 59 men on HMCS Alberni killed. It got U-480 through 3 patrols in the most heavily defended waters in the world before a mine finally caught her. It proved that a fisherman's net, reimagined in synthetic rubber and tuned to acoustic frequencies, could make a submarine invisible, and sometimes in war, as in science, proving something is possible is all that matters. Someone else will make it practical. Someone else will refine it, improve it, turn it from a desperate wartime measure into standard technology. But the first person to prove it works, to show that the impossible is merely difficult, that person changes everything. Erwin Meyer, working in wartime Germany, surrounded by a collapsing regime and an unwinnable war, proved that submarines could be made invisible to sonar. He did not win the war. He did not save the U-boat fleet from destruction. But he changed what was possible. And that change echoes, quite literally, through every submarine that sails today, coated in acoustic tiles that owe their existence to a simple insight about rubber, air, and holes arranged just right. Sometimes the most revolutionary ideas look absurdly simple. Sometimes they look like a fishing net stretched over a submarine. And sometimes that simplicity is exactly what makes them work.